Hello again, December 16th, problem 22. Having misread a problem or a question in problem 20, namely question 20e, I am very careful reading the problem now. The first was this base field, what might that be? And as we see, it will be specified in the questions. So it can be any field of any characteristic, though we are only working with characteristic 2 here. And that means that this linear translation, which we, of course, was the first I thought about here, adding a squared divided by 4, that won't work in a characteristic 2 field. All right, let's get started. First, smooth at all points, and let's work projectively. So I won't write f tilde, just write f. And then the partial derivatives. So when do all these guys vanish? That's the question. This one gives x equals 0. Then we are done with x. Here we can put y in, not just right. We can set z and here y outside the parenthesis. That gives certain possibilities. Just going one. Y equals z equals 0 is impossible, because x vanishes as well. We can't have all vanish. Then z is 0 and y equals 2az, which is then 0, impossible. That was the 2 with z 0. Then we have 2y plus az vanishes, and y being 0. That implies z vanishes as all. That's impossible. So the only possibility is 2y plus az vanishes and y plus 2az vanishes. The determinant is 4a minus a, 3a. If a vanishes, then we have the point 0.0, So that's one possibility. Or they say, yeah, smooth is the opposite. That was one possibility. And the other one is that the characteristic is 3 char k equals 3. Then what? Then these two are equivalent, and we do have a solution. So let it be given z, y equals minus 2a z, and let's put that into the equation. Y squared z, that's 4a squared z squared times z plus a y, that's a minus 2a squared z to the third equals 2a squared z to the third that may have solutions. Well, the conclusion is that if the characteristic of k is distinct from 3, then all points are smooth, and a distinct from 0. Then I need to find out characteristic 3. Can I find such a point? And we would like to have an obvious, no, we can't do that. Well, let's just set z equal to 1. If we have a solution here, then it vanishes. And when will we have a solution? Now we are in any field. So I guess the condition is that 2a squared is a cube. character k. That's my answer to question A. Now we choose a specific k, power of r, and then show that this is the number of points. It looks like one of the maps, y maps to this, or x maps to x cubed, is 1-to-1. And R is odd. Interesting. So let's see. 2 is, of course, equivalent to 2 modulo 3. So 2 to the rth. Because r is odd, and therefore is 1-to-1. And going affine, that means that every y maps to 1 left-hand side, which maps to 1x, because it's onto and 1-to-1. Finite field, it has to be onto. We've had all this before. And we still have the point at infinity. Here we have the equation. If z equals 0, x must be 0, so the only point at infinity is this gives 2 to r, and at infinity as we're used to. So altogether, the number of points equals 2 to rth plus 1. That was B. And now 22C. I'll take a break before starting on that, and even take an early coffee or something. All right, let's do as we have done with the others. So this is the curve C and the number of points in C. We are going to use the usual formula. Where we sum over characters of order n. And it holds provided alpha is non-vanishing. And I will use that to the left-hand side and right-hand side. but then it doesn't work if one of them one of them vanishes. So let's start with x vanishing. And here we have y vanishing also. Oh, if one of them vanishes, then x to the third, that needs to be naught, of course, my God. So if the left-hand side vanishes, then x needs to be naught, and vice versa. That's just equal to alpha times the number of solutions to x to the third equals alpha. And here we have 2 points, namely naught and minus a, so that equals 2. And here we of course sum over alpha distinct from naught. And here we have the first problem. This is not a power. Could it be that it's 1-to-1? Of course it's not. Naught and minus alpha maps to the same value, namely naught. So it's rather 2-to-1. I guess this was why I needed the break, because I anticipated that we would run into a problem here. And having had my coffee and chocolate didn't really help. All right. Well, a few minutes passed, and I thought about this being 1-to-1 once again. And it occurred to me that in general, x going to x squared is 1-to-1. So maybe this one is in general. The multiplicative group has an odd number of elements, so x mapping to y mapping to y squared is in general, or is 1-to-1, reflecting there's no character of exact order 2. Well, let's check it. That's the question. So let's go back to basics. In this case, they are equal. I'll just note again, we have characteristic k being 2. So that's one possibility, and this is the other one. So if A is distinct from naught, it is 2 to 1. Except when A is naught. That's very weird. No, it's not, because we have an even number of points. So it's 2 to 1. So I'm still stuck. I got a new idea, and that was to make this one run over what it might be, and then solve for y squared, and y squared is 1 to 1, so there's 1 every time we get a value here. This seems very odd. I'll just write up what I thought more concretely. Nah, that's nonsense, I think. I wanted to let this guy be free, and then for each result solve over y. But y will always already be fixed if I do this. That's nonsense. Maybe I've been overthinking this. Oh, let's go back a little. Oh, that was over here. I'll just erase them. Now what do you think? We just sum over all y distinct from alpha and naught. And then where that's naught, there are the two possibilities. And this is then equal to the sum what's that? There we go. Of y squared plus alpha y. And that's a plus. And this is where I need to be very careful. Well, in these two cases, this vanishes anyway, so we can remove that condition and sum over all y's. And we need to solve over the one chi3 and the conjugated or inverse and the trivial character. Now the trivial character, the sum over all the guys gives naught. The trivial character, that was not it. The trivial character gives unity for all, so it's just counting the number of points. And that's 4 to the rth minus naught and alpha. So that's minus 2. So here we retrieve them again. Let's work on this guy. And to express it like the j, we need to have 1 minus, so we set alpha outside and change sign on y, but that's basically the same here. Minus 1 is just 1, so there's no problem. So it's alpha squared, we take out chi3 of alpha squared. there we go. Now I'm slowly approaching a result. 4 to rth, and it's still only the affine points I'm counting, so we need to add 1 to get the result in the problem. Plus of a, this should be, no, it should be a all the way through. Yeah. So where should we end? Oh my God, success. In the situation of part C, show that, so we should be able to explicitly evaluate J of chi3 point chi3. I think it's time to invoke problem, was it 6 once again? There we go. So this is equal to chi3 bar of 4 times j chi2 chi3. But chi2, oh, what if it doesn't exist? Let it be that if it is the non-trivial character, and it isn't, that means we have to go through the same stuff as we did in the derivation of it. I'll need to go back to look at my derivation. This calls for a larger break. Good morning, December 17th. I had worked myself down a rabbit hole in question D, trying to use the definition. Then I thought of this formula and said, okay, we can compute G, and maybe we can compute G explicitly, but that would be more complicated. And then I thought, well, we can do it for the base field Q equals 4. And then I got the idea finally to use Hasse-Davenport relation to get the G's. I should have written that as well, of course, in preparation. The field has 4 elements. And this is the minimal polynomial of the u's. So the trace of u is 1. And that means psi is 1 and minus 1. And chi3, we say this one is omega, omega bar, unity, and naught. Omega plus omega bar, that gives minus unity. That was not what I expected. Of course, if they both give minus 1 and then we add 1, then it should be the product. So that's clear, that's clear. As far as I recall, the norm of, or the modulo of G should be 2 square root Q Well, let's compute J explicitly and then see whether it adds up. Oh, it couldn't. That would be a fraction. Well, let's just do it anyway. I'll just remove myself a little. 1 minus x it's 1 naught u plus 1 u chi of 1 minus x 1 naught omega bar omega so we multiply these two, that's unity plus unity. That equals 2. That makes sense. And now that I come to think of it, if G was, say, minus 2, or should we just say a 2 to the third, that's 8 divided by 4. So this is the guy I must say, this guy is wrong. I'll just make a break and then find the error, and then we can continue using the Hesse-Davenport relation. Well, that was easy. I used in computation of G of chi3, I used this line and this line. I have to use these two lines. So it becomes unity minus omega bar equals 2. So now it's correct. Next, we should use the Hesse-Davenport relation, which I should have written still. Here we've got it. So when we are in k equals f4 to rth. Then we have the base guy here. So g of and that's the one we need. Equals minus and chi of g of chi here equals 2, so that's minus 2. To the rth. And that means that j equals, and then that's to the third, so it's minus 2 3r divided by 4 to the rth. That takes care of 2 r's here, so we are left with minus 2 to the minus 2 to the rth. If r is 1, that gives 2. All right, then let's see what I had to derive. That's the same. Or is it? Minus to the rth, so it's minus to r minus 1, 2 to the rth. Is that what it said? Right. That was D. Then we shall find the zeta function. Now we have dA, so we should use our formula for which we have here. Chi3 of unity, A was set equal to unity, so chi3 gives unity. Let's just make a new section here. NR equals 4 to rth plus 1 plus then we use this formula. Minus 2 to rth, and where was it? It's here. And then the complex conjugate, which is the same, so it's just a factor 2. And then we can use problem 2 of section 1 to write up the zeta function. In the numerator, we have this. So it's 1 plus 2t squared divided by 1. Now I forget it. It's quite some time ago we've had it. minus, well, I knew it was minus up here, so it's minus 40, and then it's unity, so it's 1 minus t. All right. And now for the final question. That was what I thought we could do. We should start with a translation here. A equals 1, and then we just do it on a new page. So we add a quarter on each side. No, we do not. We multiply it by 4 first, and then we add 1. Now what's that? 4x to the third. A change with coefficients in Q I thought this one would be trivial. Let's try to generalize it. So we write y as, I don't want to y mark, that's too. So what can we use? U plus a, x equals v plus b. We should also have a coefficient on, yeah, oh my god. Silly, silly, silly. So let's put a coefficient on x and see if we can do it that way. And then hope that the coefficient to u becomes a square. Now this is silly, because then a needs to be minus a half. So we must put a c on here as well. like it. Maybe this is more difficult than I anticipated. Now let's try this first. This guy we need to get rid of. So a is minus 1/2. Anyway, I don't think I've come anywhere closer to solving this problem that we don't get a cube there. I've just made it more complicated without really solving anything. I won't waste your time with that, so I'll make a break where I just try this to make sure it goes wrong as I anticipate, and then see if I get another idea. Well, here I inserted a equals minus 1/2. Then we get this equation in u and v. And now if c squared equals b to the third, that is actually possible. And if they want to have unity here, that can be done in many ways, of course. We needed 16 here, so that tells us what c must be. And this is possible if b equals 2. So the change of variable is to set y equal to 1h y mark minus 1/2 and z equal to 2 z mark. And of course they can be solved, so that's the linear transformation of variables, or the inverse one anyway. That finishes my answer to question 22.